KMnO4, right? It's concentrated, which means we're doing our oxidative cleavage.
Yes.
Yes. So which double bond are we stretching? I see 4 of them.
One outside of the benzene ring.
Why outside the ring and not the ones inside? Benzene rings are stable. There's resonance. Those aren't formally a nonpolar pi bond. They're something less than that non-polar pi bond. So we could draw out our ring again, stretch it, stretch. This time I could stretch it a little bit further. Erase the middle of it, draw on the oxygens, and then decide, do we have hydrogens attached to those carbons? Do I have the left product? The one with the benzene? Yes. Okay. So what do I do? Place it with an OH. How about the right one? You're saying yeah? Okay, good. You and I can have a conversation. Everybody else can go away. Okay? Yeah? Right there? So we should replace that with an OH. Okay? You good? Is that your final answer? Crap, there's another hydrogen. What do I do? Do the same thing. Is that a correct final answer? No, unfortunately, that happens to be H2CO3, which you should remember from Gen Chem and from first semester OChem lab. What does it do?
Decomposes into water.
Immediately decomposes into CO2. We got the carbon in the middle. So we're still removing those hydrogens. We're still replacing them with oxygen. We typically end with an acid on our organic compounds because the other position is a carbon. Okay? If both positions are hydrogens, we have to replace both of them with oxygen bonds. It just turns out that the oxygen I'm replacing them with is the same oxygen. So you still end at the CO2. You guys get that? You guys want a little time on the next one to do it on your own, or should we work through that one together too? Okay, unfortunately, because we're tight on time, I'm going to take that to mean you want my help. So we'll stretch. Why do we have to stretch the double bonds within the ring this time? What's that? There's no resonance. Okay? Remember, the benzene ring, just because we have double bonds in the ring, doesn't mean they're magically stable. Okay? It's because we have a benzene ring that those pi bonds were stable. We don't have a benzene ring anymore. We have technically a cyclohexadiene. Help, right? I'm dying. Clearly I am. Jokes are falling deaf ears. Oxygen, 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 oxygen. Yeah? Okay. Do I have hydrogens?
Yes.
Yep. So we'll slide those out, draw in our acids. Do we have our final answer? Okay, I got a no from one person. Anybody else? It's a no. Why is it a no?
Because you have the alkyne.
We have the alkyne. It's still a nonpolar pi bond, which means I still need to strip that one, draw in my oxygen to replace it. Can I have a triple bond to an oxygen? Technically no, which means how do I get my third bond to an oxygen? I bring in another oxygen. What happens with the other piece? Now in blue. I don't accept carbonic acid. Carbonic acid is unstable, immediately decomposes. CO2. Okay. This is a favorite on the ACS exam, looking at these oxidative cleavages. Because what they'll do is they'll give you the products and say which of the starting materials could possibly make these products, and only these products. Okay, so it's recognizing where those bonds break and how we parallel and break those systems apart. Okay? So for this one, we would need 1, 2, 3 products come out of it. They've also done that. Okay? We've run this reaction. How many products do you get? 1, 2, 3, 4, 5. Technically 4, because it's ACS. Okay? And that could be a trick question because it's a symmetrical molecule and you only get one product even though you're cleaving and making 2 things. But those 2 things are the same or identical. Okay? Kind of make sense?
Question.
Yeah.
What if the double bonds inside the ring were conjugated?
If they're conjugated, I believe they will still react. Okay? We need the cyclic structure of that conjugation to actually hold it. What will probably happen is they will react slowly at first, and then once you cleave one, the other one's now ripe for pickings because it no longer has that conjugation.
Thank you.
Okay? So we good? Is that a question?
No.
No?
At the risk of sounding dumb.
No, go for it. I do it every day.
What would conjugated mean exactly?
Okay. So conjugated is saying that we have the pi bonds set up so that they can do resonance with each other. Okay. So the benzene ring has lots of conjugation. Okay. And this is a neat way to answer Farzan's question too. What if they're conjugated? What is right here? Can I do resonance there? Yeah. There is conjugation even in that system onto that last pi bond. Does it still react? Yes. Okay. So even if they are conjugated, they will react. It's that extra cyclic conjugation that makes it aromatic, which you might be like, well, that's what I've always called those. It actually means something, but we won't address that meaning until the end of the semester. Okay? Other questions? Okay. Get it? The ozone oxidizing agent? Other, except it's ozone. Yeah. Perfect time. Perfect timing. Ozone, O3, is an oxidizing agent as well. Okay? It has a little extra bonus beyond the permanganate. Permanganate just oxidizes, okay? And it doesn't really stop. Okay? If it's cold, it stops at the diols. We get no cleavage. If it's hot, it completely oxidizes all the way down. So we get rid of any hydrogens and turn them into oxygen bonds. Okay? But what if you wanted to say stop at an aldehyde? Okay, there's still a hydrogen there. Aldehydes have distinctly different chemistry than carboxylic acids. Okay, so I may want to stop at an aldehyde. Permanganate can't stop at the aldehyde. So this is where we can bring in other oxidizing agents, and this is the added benefit, if you will, of ozone. So when we go through and take a look at ozone, it does the same kind of cyclic chemistry that we saw with all the other additions. Okay, your pi bond comes out, attacks an oxygen. This causes a charge to be removed from that positive one. The negative oxygen can come back in, leaving us with a 1, 2, 3, 4, 5 center ring, roughly equivalent to a cyclopentane. Okay. Then we get 2 oxygen-oxygen bonds. Are oxygen-oxygen bonds particularly stable? No. So what happens? Well, that happens. Some weird chemistry happens where that ring breaks open and the oxygens pretty much play a game of shuffle the cards. Okay? And the oxygens shuttle around to end at what's known as the ozonide, okay, in the lower left-hand corner. That ozonide is our final kind of pseudo-stable intermediate structure. From there, we can break that apart with a step 2, which unfortunately the textbook didn't elaborate nicely here. This is a step 2, adding an extra reagent. That extra reagent can break open the ozonide. Okay. Look at the net result. There were 3 oxygens in the ozonide. How many oxygens in our final organic product? 2. What happened to the 3rd oxygen? It reacted with our other reagent, our second reagent, okay, which they've shown. It would have been nice if they'd shown the structure. Is that. So we add what is known as DMS as our step 2, DMS, where D stands for di, M, methyl, S, sulfide. Okay, so we add DMS as a reagent, which scavenges the oxygen out of the ozonide. Notice how many steps of a mechanism did they show the detail of there? They didn't, which means don't worry about it. Okay? What happens to the final product? What happened to the DMS? It scavenged that last oxygen. So it's still a D, it's still an M, it's still an S. DMSO sound familiar to anybody? Yeah, that was our nice standard solvent, polar aprotic solvent that we use back with our substitution reactions. Okay, make sense? Okay. So let's take a look at ozone again. So step 1, we're adding the ozone. Okay. Ignore that big old thing in the middle, because that's misleading. So according to step 1, just following this top box, we'd end up with the ozonide, which I don't want to draw the structure out, so we'll just write the name. Like goofy 5-membered ring with our oxygens in it, right? Okay. Step 2. Notice this one's a little bit different than the one we just saw. How is this one different than the previous slide? The previous slide was DMS, no oxygen. So it could scavenge oxygen. What does H2O2 have?
Oxygen.
Oxygen. What do you think is going to happen if we used H2O2 instead of DMS? Now it will fully oxidize. Okay? So we'll go from the ozonide down to our carboxylic acid, as opposed to on the previous slide. Whoops. Previous slide, what did we end with? The aldehyde. Okay? So ozone is useful in that same kind of oxidative cleavage process that we saw with permanganate. Okay? Where it kind of stands out as an extra reagent is that we can stop it at the aldehyde. Okay? Which is really synthetically the only reason we would use ozone. We would just stop at the aldehyde. Okay? Because if we wanted the carboxylic acid, we would just dump in the permanganate and run with it. Okay? Kind of makes sense? Okay. So, your 2-step process, oxidative addition of your ozone to the pi bond, that forms our ozonide. Okay. As far as memorizing the structure of what the ozonide looks like, what do you guys think? Is it something that's worth trying to memorize? Why are you saying no? How many times did you see me draw it? Oh, I didn't. That's because it's not worth memorizing. Okay? It's not worth that extra step to deal with it. What you really need to get out of it is, unfortunately, the reagent. So once you form the ozonide, then you've got the cleavage. And this is where we run into weird terms. We refer to it as the reductive cleavage, okay, or the oxidative cleavage. In both cases, what type of reaction did you perform to the carbon structure? Both cases, it was cleavage. In both cases, it was oxidation. I still added oxygen. So why am I referring to it as a reductive system?
Because you're still taking away an oxygen.
No, I'm still adding oxygen.
Because you don't fully oxidize.
I don't fully oxidize it. Okay? So the oxidation really has 2 stages, step 1 and step 2. Both of them are oxidations. The reductive one is I only take 1 step in the oxidation. I'm not doing a reduction by any means. We're still adding oxygen. I'm just not adding as many oxygen as I could add. Okay? The oxidative is we just pushed it all the way. Very few exceptions on the reductive reagents. For the most part, I've only seen DMS as a reagent for the reductive step. For the oxidative step, that one gets a bit frustrating. Peroxide I've also seen water, and I don't know if that was a typo on their part, or if water would do it. Probably would. That ozone structure, the ozonide, wants to fall apart. Okay? So if you're seeing oxygen at all in that second step, make it oxidative. Okay? If you see no oxygen in that second step of ozone, you can keep it reductive. Make sense? Okay. Which kind of segues nicely into now the complete opposite reaction, reduction. Okay. Again, this is formally a review, so we don't want to spend a whole lot of time on it. I do like this slide, okay, or this image. We're looking at adding hydrogen. And if we look at the reagents for adding hydrogen, we've got that issue with our projector screening. We've got H2, H2, H2. Ooh, weird. Okay. The most common thing being added, though, is H2. Have we seen elemental species being added to pi bonds in other cases? Ozone I won't quite accept as elemental. Technically, we run into weirdness on that. Bromine, Br2. Okay, when we added Br2, did we need an extra piece? Notice in all of these cases we have an extra piece. Did Br2 need an extra piece to add? No. Why did Br2 not need a piece, but hydrogen does? What's that? Bromine is large, which means when I bring in that single bromine atom, it can coordinate to both carbons of the alkene, forming that cyclic bromonium ion. Hydrogen, on the other hand, is so tiny that hydrogen cannot bridge that gap, which means I can't formalize that cyclic structure. It is also so small that if I just tried to bring hydrogen straight down to it, it also can't make the connection. So something else needs to be added to help hydrogen interact with those carbons to facilitate it. That's where the metal comes in. And that's why I like this slide. We've got the green surface representing our metal. Hydrogen gas will coordinate to it. The alkene or alkyne will coordinate to that surface as well. Okay. Now that they're both locked onto the same plane, now we can start to have them interact with each other, and the hydrogen can come in. Because it's now coordinated to the surface, though, in our key step down here, insanely tiny, we no longer have a pi bond. What do we have connecting those two carbons? A sigma bond. And theoretically, a sigma bond could rotate. Interestingly enough, in this case, it can't. It is too pinned by the substrate, by that metal surface, that it cannot rotate. That means when the hydrogen comes in from one side and the hydrogen comes in from the other side, they are both being added to the same side of the pi bond. So we get either potentially the cis product, but it's really doing a syn addition. We're adding the hydrogens to the same side of the pi bond. That syn addition becomes super important for stereochemical reasons. Okay? Kind of makes sense? Palladium, platinum, nickel, Lindlar catalyst. Why would I choose one over the other? They do slightly different things depending on the reagent we're working with. All of them are a metal surface, okay, coordinating the hydrogen and coordinating our pi bond. But they have varying abilities to coordinate pi bonds. Why might that be important for us? Are all pi bonds the same? No. Name 3. You should be able to get 2 pretty quickly. Come on. Alkene, yes. Alkyne, yes. Way to pick the 2 easy ones. Are there other pi bonds? Yes, because I said there's at least one more. I said nothing about the polarity of said pi bond.
Lone pairs?
No, lone pairs is not a pi bond. What is a pi bond? How would I draw it?
2 lines.
2 lines. Okay. We had one case, alkene. That's a non-polar pi bond. What other kind of pi bond could I get? How about a polar pi bond? How about we bond carbon, because this is an organic class, with oxygen? We now have carbonyl. Okay? Carbonyls can also react with these surfaces. Okay? Depending on the functionality, we may see that continue through. Okay? That is something we'll evaluate when we look at our carbonyl chemistry. Okay? Alkynes become a little bit tricky. Okay? This is where Lindlar's catalyst comes in. Lindlar's catalyst, interestingly enough, will not react with what? Okay, remember, we're only looking at two functional groups, alkenes and alkynes. Okay, it won't react with the alkene. How do you know that?
Because that's the final product.
Okay, we take a look at the final product for that reaction. It has an alkene in it, which means Lindlar's better not react with alkenes, otherwise we wouldn't have that as a product. Or two, I said there were two possible answers, right? We know the alkyne works, which means, whoop, wrong finger, sorry. I thought it was the other hand, I swear. Also good timing. We end up with the alkene, okay, as our leftover choice. Okay? So H2 and palladium, H2 and Raney nickel will both react with alkenes and alkynes. They will fully add hydrogen to them, which means we end up with the saturated structure, no more pi bonds, period. Lindlar's catalyst will not react with alkenes. It will only react with alkynes. But because it is, again, still a metal, the hydrogens get added to the same side of the pi bond. What does that mean the two carbons must do? Be on the same side, which means my final alkene product has what geometry? Geometry is a bad word, but we have a cis product out of it. We have the cis configuration. Configuration, good call. That was a much better word. Okay. What happens when we move to the next one down? What is interesting about that product? It's trans. That might be thermodynamically more favorable, but we can't form the trans when we add just elemental hydrogen because the hydrogens have to go on the same side, and we can't get that with that bottom case. What's going on with that bottom case even further that looks a bit bizarre? Do you see H2? No. Okay. What do we see that's reactive? Okay. We have NH3. Okay. And a couple of people from tutoring center can tell me about the pKa of NH3. What is the pKa of NH3? 35, 36. Really, 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 really high, meaning those hydrogens are not acidic is a good answer. The nitrogen is basic, and those hydrogens are stuck to the nitrogen. Well, then how do I get hydrogens onto the structure? Not from ammonia, or at least not immediately from ammonia. What is the other reagent? Sodium. But every time we've seen sodium in this class, what have I done? I've ignored it or erased it. Why will I not ever ignore or erase that sodium? Not so much that it's reacting with the nitrogen. Would you say that?
It's a solid.
It's a solid. What does that mean? Why is this sodium different from, say, sodium hydroxide? That's a solid too, and I will still ignore that sodium. What is different about the sodium I've got written there?
It's not charged.
Say that again?
It's not charged.
The sodium in our reaction is not charged. The sodium in sodium hydroxide is charged. The sodium in our sodium hydroxide is a counterion to weakly stabilize the hydroxide. The sodium in the reaction is elemental sodium. Okay? What is our standard state for sodium? When you think about sodium, do you think about seeing it chilling around as a solid? No, why not? It's insanely reactive. It does not want to exist as a solid. It wants to become charged. It does that by ditching an electron. We're looking at elemental sodium, effectively a free radical. That electron needs to get dumped someplace. Where's the highest energy thing that it can dump electrons to? help clarify. Let's erase some stuff.
H3.
Where can nitrogen hold those electrons? How many electrons are currently around the nitrogen? 8. How many more electrons can nitrogen fit? None. So it's not going to the nitrogen. Well, shoot. Where can it go? Rhymes with fly. And by. What?
Pi bond.
We have a pi bond. What can happen? Single electrons come out. And what do we form? I have a radical and I have an anion. As that structure breaks apart, it's going to find the lowest energy state possible. Why is it going to try and find the lowest energy state possible? So it can be as stable as possible. It's a radical and an anion. Is it stable? No. It is insanely unstable. So what it is going to do is force those R groups to get as far away from each other as possible. There's your trans configuration. We said ammonia, not acidic. What can you tell me about a radically charged carbon anion?
Very basic.
Insanely basic. So insanely basic, it can make ammonia act as an acid. And the result is that it will remove a hydrogen from that structure. We'll end up now with our hydrogen attached. I still have a radical. That is still unstable. What does it do? Finds another sodium to form another anion. The other anion can react with hydrogen yet again on another NH3 to give you your trans final product. The pi bond of the alkene is now just barely low enough in energy that it won't react with the sodium again. Okay? That is the only way that you will get a trans double bond in a reduction. That is why the ammonia and sodium metal reagent is very, very common on the ACS exam because it's different from most of the reductions. It gives you the trans product instead of the cis. Okay? So it is a big key one to remember. Make sense? Questions? Okay. I believe, what we've got here is the summary. So you can see what happens. H2 and platinum or palladium with nickel. We'll go through and do our reduction. Notice that we're getting the syn product coming out of it, or a syn addition, cis product. If we take Lindlar's catalyst and sodium with an alkyne, we can take that across to our pi bonds. So it's just the summary slide. Okay. Here's our sodium metal mechanism if you wanted to see it. It's all neat and drawn out there as opposed to the kind of cruddy version that I hand drew. If you've got the slides, all you got to do is pull up this slide and click in the white space and then hit delete. Okay, and the image should appear. Are you looking at it, Jenna? Did it work?
I don't know what you said to do.
Oh, didn't have to worry about it. It was already there. We will see this again with benzene rings. What is the result with benzene when I take sodium metal and ammonia? Oh, look at that. It also did a reduction. You might say, but weren't benzene rings incredibly stable and shouldn't react? Yes, you're right. Sodium metal really doesn't want to stay a metal. Really wants to become an ion. That's what initiates the cascade to do the reduction of the benzene rings. That reaction, again, we wouldn't expect it to happen because it's an aromatic ring, right? So if it isn't predicted to happen but does happen, what do we do? What's that?
Assume it's a radical.
Sort of, yes, fair enough. Someone gets credit for it.
It gets named after someone.
It gets named after someone. It's known as the Birch reduction. Okay. So we will see that at the end. More important for today is looking into chapter 10. Okay. This is now officially all new-ish, new-ish stuff. When we're looking at our substitution and elimination reactions, in first semester, we didn't really look at useful reagents. We picked reagents and conditions that would allow us to learn what substitution was and what elimination was. Okay? So in chapter 10, it goes through and says, well, this reagent is better at doing this for this reason. This reagent is better at doing this for this reason. So it's a lot more reagent-based on how it functions. And a lot of it comes down to what you're looking at within your structure. So in substitution and elimination, both of them are following the same basic characteristics that are outlined up above. I want you to identify those basic pieces for me. And basic is being used not as a reagent word, but as a component word. What are the components that we should be looking at within a substitution and elimination reaction?
Substrate.
We have the substrate. What else should we be looking at? Okay. We have a good leaving group. Whoops, I'm going to put that about here. What else do we have? But I said substitution and elimination. Do I want a nucleophile for an elimination?
Or base.
I want a base. Okay. Why are those both drawn in red?
Are they the same?
What is the definition of a nucleophile?
Electrons, wants to give electrons.
Electron donor, more specifically to,
Electron.
what's that? To an electrophile. Yes, but let's not use that. Electron poor is too broad. So we've gotten too specific and too broad. I want somewhere right in the middle. Come on, Goldilocks it for me.
What's acid?
Too broad. Two words ish. Was the superscript giving it away? Not hydrogen, not H+. What does the base do? Well, it's also an electron donor. That becomes a problem. Bases and nucleophiles are very easy to get confused. So we have to be very careful with how we apply them. What is the final definition for our base? Electron donor to hydrogen. Okay? By having that delineation, that can help us differentiate and decide what we're looking at. Okay? There's one last thing that we need to be looking for when we look at our substitution and eliminations.
Solvent?
The solvent effect. I have them listed on this slide right now in order of importance. Almost. I would actually argue nucleophile and base should be the very first thing you look for. Then you can move to substrate. Then you can move to leaving group. Yeah, and then you can move to solvent. Okay. We love our projectors in here, right? In theory, someone's working on that. Yeah. If you watch the video, it'll show up. Okay. So chapter 10 goes through and says, well, how can I make a better leaving group? Okay. How can I make better nucleophiles? What are amines and substitution do for us? Okay. And then how can I make better nucleophiles in general? So we're looking at different ways to approach the individual pieces of substitution and elimination and how do those things shift out. Okay. So oxygen in substitution and elimination. So we take a look. We've got what functional group shown? It's an alcohol. Right? If we're going to look at an individual structure of an alcohol, we need to say, what can it do? Okay? Why is oxygen synthetically useful? Said another way, oxygen is synthetically useful due to its lone pairs. Okay? And that makes it useful as what? That's what that line is supposed to mean. It could act as a nucleophile or a base. Okay? And due to its electronegativity, what can it do? Steal electrons from what?
Bonds.
What bonds?
The oxygen, hydrogen bond.
It can take electrons from the hydrogen, meaning the alcohol can act as an acid. And Wyatt, as you continue to talk, you said it could steal electrons from carbon, which means the alcohol functional group can act as let's not do leaving group. We're focusing on the chemistry that's happening. It's the carbon. So we're looking at it acting as an electrophile. Anybody have any problems with a single functional group being able to react as all four of our major categories? Okay, that's a bit problematic because if I now mix it with a reagent, that reagent could take me into one of four very different directions. So I have to be a little bit more careful when I look at alcohols. That means if I want to do something with an alcohol, I may very well go through and change it to a different functional group so that I don't have to worry about everything happening at once. Okay? What could I convert it to so that it isn't quite as crazy? What's that? Okay, we could try and convert it to an aldehyde. In the aldehyde form, what happens to my chemistry? Can it act as an acid anymore? Not as easily. Okay. Can it act as a base? Again, not as easily. Okay. It still has it there, but it's a lot more occupied with that carbon. What happened to the carbon?
Gain a p orbital.
Okay, it has that p orbital. Is that a p orbital where the electrons are really equally being shared with that carbon? No. So I may have added 2 bonds to that carbon, saying, oh, well, now it can't act as an electrophile, but the 2 bonds I added are both to a more electronegative element. When we look at the aldehyde functional group, we see primarily an electrophile. Admittedly, I did not see you going down that path, because that's not the path we're looking at. But that is a valid path. So let's try again. What else could we convert it to? Remember, we were looking at the context of substitution and elimination. What could I substitute the OH for that would not be as drastically reactive? What could I put in there instead of the hydrogen, or sorry, the oxygen, that I wouldn't have the hydrogen anymore? How about any of our halogens? Okay. So we can do subtle tweaks to our structure through substitution. What if I wanted to get rid of that functionality altogether? In an elimination, what would I need to do? Convert it to? An elimination results in a what? A pi bond. Is it a long weekend? Yeah, just checking. Okay. So what we're looking at with the alcohol functionality is how can we tweak and change it. So if we look at all of our reactions, okay, these aren't all of them, but these are some of the bigger ones that you've already seen. HBr. Okay. To get the bromine on, I also have to add it with hydrogen. Why can't I add just sodium bromide? The OH isn't a good leaving group. So by adding HBr, I'm adding a hydrogen that can make that oxygen no longer basic, and now it's charged. It didn't want to be there, so it can leave. The bromide can then come in. Same deal with HI, putting in the iodine. Move up to HCl. Notice I've added an extra step, a zinc chloride. Why do I add that extra piece? What is different about HCl as opposed to HI and HBr? Chlorine, good step, has to do with size. Okay? It has to do with the nucleophilic characteristics of the chlorine. it's not quite as good a nucleophile as the iodide or the bromide, which means it needs a little bit more help. Here's zinc chloride. Okay? We flip to the other side. If we add just straight up strong acid, but we dilute it, so sulfuric acid. How is sulfuric acid different from HCl, HI, and HBr? The conjugate base is not a good nucleophile. So H2SO4 doesn't give me a nucleophile. But I did a substitution, didn't I? Where's the nucleophile? Itself. Remember, when we run a reaction, we may draw only one molecule, but we have to remember there's not only one molecule, there's billions upon billions of molecules. Okay? So if I add just a dilute acid, I can turn an alcohol into a good leaving group. Just being in the presence of that alcohol can cause it to do a substitution, and I can get a, said better, an ether. What is special about the ether that is different from the alcohol? Ethers are virtually unreactive. Okay? Why? Does it have a hydrogen anymore? Nope, so it can't act as an acid. We've lost that. We do still have that electrophilic ability at the carbons, but they're also now massively sterically hindered. That oxygen acting as a base is even more sterically hindered, being in the middle of all those carbons. So the ether functionality now drops through the floor. So if I'm trying to neutralize the reactivity of an alcohol, an ether is a good call. If I add, instead of dilute sulfuric acid, now concentrated sulfuric acid, now I end up at an alkene. Why does the sudden change in the concentration make all the difference?
You will weaken the nucleophilic ability of oxygen.
Dilute acid means I make a good leaving group, right? But I still have tons of alcohol present. Concentrated means every single alcohol has been protonated. That's why it's concentrated. If every single alcohol is protonated, do I have a nucleophile? No. Where do I get the electrons to stabilize that oxygen? If I can't go from outside, I have to go from within. There's the formation of the pi bond. Okay? So, activation of our leaving groups. General acid, okay, as opposed to major acid. We look at our reaction here. What's the most reactive thing you see? Right? We see the oxygen being reactive, so let's get rid of that HA and make it HI. What's the most reactive thing you see? Okay, now the acid. Okay? I like where you pointed with the alcohol. That's fair. Okay, but if we now specify that that's really actually a strong acid. This is where we'd run my so-called face test. Acid or alcohol, which do you want splashed in your face? The alcohol probably wasn't that bad. That might have been this weekend. Okay. The acid will hopefully never, ever, ever happen, because that's unpleasant. That means it's the reactive one. What makes it reactive? The positive proton on the hydrogen. So what I'm thinking about when I see this is I see H plus with HI. I need to neutralize the H plus by finding, what did you say, Jenna? The lone pairs on the oxygen. So we'll still circle back to that answer, but that wasn't the primary focus. We have to focus first on our most reactive thing, not, oh, we're working with alcohol, so let's make the alcohol react. Right? That works in most classes. That works questionably with OChem, and it works horribly with how I teach it. Okay? Focus on the reagents. If we put that hydrogen on, what we should end up with would be this structure. Notice there is a positive charge. 9 times out of 10, you will forget that. Please stop. Okay? Put the charge on. Always, always, always. Draw a product and then say, Mike said I got to check for charge. Check for charge. Okay? Do that until you're blue in the face. So that structure now neutralized the acid, but now what do I have as a problem? I have a positively charged oxygen. Does oxygen want to be positive? No, so it has to find electrons. The easiest place to find electrons would be, what's that? We could pull from the carbon-oxygen. We could pull from the carbon-hydrogen. Why is the carbon-hydrogen not the best? I just made that bond. Okay, it takes me backwards. It's not necessarily a bad thing, but we have to be cognizant of it. Okay? If I take the electrons from the carbon-oxygen, though, then I'd have a positive carbon. Am I allowed to have a positive carbon? It's fair. Depends on the mechanism. If I'm running under an SN1, can I have a carbocation? Yes. Okay, for those of you being, I don't remember what SN1 was. Please go back and review first semester. Feel free to sit down with me and nail that out. When I say SN1, you say carbocation. When I say SN2, you say no carbocation kind of works. Let's try another one. Backside attack. Okay? By nailing just those two correlations, the rest of the predictions of what you need to expect for SN1 and SN2 can be somewhat derived from those two ideas. Okay? And you need to have those ideas relatively quickly at hand. Okay? So how are we going to decide what happens with this potential carbocation? Because that's a positive charge. I don't want a positive charge. So what do I do? What would I need to do? I need electrons. Am I in an environment where I have electrons that are willing to be shared? Yes, share them. If I'm not, where do I get electrons? We said there's nothing else outside.
Go inside?
Go inside and do the elimination. So what we've got to do is look at that A minus. What is it? If A minus is a nucleophile, what happens? It can attack that carbon, and we run our substitution. If A minus is not a nucleophile, it can't do that substitution. Okay? Depending on the mechanism, remember carbocation? Carbocation was tied to which three letters? Carbocation is SN1. We're moving the SN1 downwards, potentially, and we're doing the SN2 upwards. Anybody notice anything odd about where I drew A for the SN2? I know it's kind of a bizarre statement. Why did I not draw it up here? Because backside attack. Okay? Even though there is no stereochemistry for that individual position, what I'm trying to do is accent that information and lend credence to it so that if for some reason I'm like, oh crap, I've got stereochemistry, I now have it already set in that direction where I can now evaluate it correctly, as opposed to having to redraw the whole thing. Okay? We said SN1, meaning water just leaves, and we have the carbocation. But again, what is A? If A is not a nucleophile, okay, or if it is a nucleophile, like I minus is a great nucleophile. What about Br minus? Good nucleophile. Cl minus, pretty good one. SO4 minus 2. It has even more charge. Shouldn't it be more nucleophilic? Well, big wasn't bad. Iodide was big, and it was a good nucleophile. Resonance within the sulfate causes the electrons to be stuck within the structure, not on the outside. That prevents SO4 minus 2 from acting as a nucleophile. Okay. So if it is SO4 minus 2, well, then I'm going to end up with two potential branches coming out of this. Okay. Where one, I do the substitution. Hey, A was iodide, bromide, or chloride. But what if A was the SO4 minus 2, or sulfate? We end up moving down into the elimination branch because I don't have electrons from outside the structure, so I must go within. And I pull those electrons from the hydrogen located at what position? That's a harder question. Most acidic, fair enough, yeah. The carbocation is located at the first position. Where's the hydrogen located? Comes after first. Second. So the hydrogen must come from the second position. But if I call things first and second, that might get confused with SN1 and SN2. So I can't call them first and second. What do I call them? It's an alternate nomenclature system to first and second. So we could try primary and secondary, but then that could be referencing the carbocation. So I don't agree with that one either.
Beta?
Alpha, beta, gamma, delta. We're at the next position to our reactivity. The reactivity source will be our alpha carbon. So we're removing the hydrogen from the beta position. Oftentimes when we talk about elimination, we refer to it as a beta elimination because we eliminated from the beta position. Okay? Some of that nomenclature for our reactions. Make sense? Hopefully it does because this should all be review. Questions? Okay. Primary mechanism for all of these moves through the one type, I should really say one type mechanism. Why might we predict the one type mechanism or unimolecular and not bimolecular? Or our SN2. This SN2 branch is rare for these conditions. I haven't specified what those atoms are, so I understand where you're going with that. If we don't specify, we're assuming those are carbons. I'm saying those can really be anything. Why would it favor the one type, either SN1 or E1, and not SN2? It's a really hard question. Substitution evaluated, substitution elimination had 4 components. What were those 4 components? Leaving group, nucleophile, substrate, and solvent. Substrate, not really different. Nothing's jumping out at us. And in fact, when you said it's tertiary, so it should be 1, I said, it could be anything. So substrate's gone. Okay? Leaving group, it's an alcohol. It's not changing at all here. We're making it a better leaving group. So leaving group's irrelevant. Substrate's gone. Leaving group's gone. Nucleophile. We have a situation where it's not even a nucleophile. Okay, so nucleophile is irrelevant. What's the only thing that stands out now? Solvent. Why would the solvent favor unimolecular? What solvent are we looking at? This is a stretch. This is a hard one. For an SN1 type reaction, we favor a polar protic solvent. Okay? We wanted that protic solvent because the counter ion, the negative charge, could be used to stabilize the carbocation, making that first step of our substitution reaction allowed to happen. Why would these conditions favor carbocation formation, unimolecular reactions, over the polar aprotic SN2? Define protic. Has hydrogen. What does HI have? Hydrogen. Not only does it have just hydrogen, it is by definition a proton because HI is a strong acid. HBr, strong acid. HCl, strong acid. H2SO4, strong acid. All of them are by definition protic, which means all of them are going to favor the unimolecular mechanism. Okay? HCl is a little bit weird. This is where we encounter our first, actually maybe even second. I think we talked about it once in first semester, but our first one this semester, classification test. Okay? The reagent zinc chloride in HCl is often known as the Lucas reagent. Right? What we would do is take a mixture of that. We take an unknown alcohol, we add that stuff to it, and we look at it. If it turns white instantly, then we know we have a tertiary alcohol. Right? Why is it changing color at all? What does that mean? It goes all the way back to 130. Chemical reaction has occurred. Well, this is HCl. What chemical reaction? Sort of fair on the acid base. Substitution. We were just looking at a substitution reaction. It's substitution. Okay? It's saying that a substitution reaction has occurred. Okay, well, HCl, just like we had on the previous slide for our substitution, right, favored the unimolecular mechanism. Which substrate favors unimolecular mechanisms? Tertiary, secondary, or primary? Tertiary. So when I take a tertiary alcohol, and yeah, there it goes, and I add the Lucas reagent to it, and I instantly see white, okay, it's that instantaneous white formation that makes me go, boom, that's a tertiary alcohol. Because tertiary alcohols react insanely fast with these strong acids. The white precipitate I'm seeing is the zinc chloride. Zinc chloride will react with the oxygen to form a zinc oxide. The zinc oxide is a white insoluble precipitate. So if I have a tertiary alcohol, boom, I see zinc oxide, I know. What if it was a primary alcohol? Well, primary shouldn't react under SN1 conditions. And since this is an SN1 condition with that strong acid, we don't expect to see that white precipitate, at least not immediately. So Lucas was able to take advantage of this chemistry and say, I'm going to use this to take an unknown sample. I don't know what it is. I'm going to add this. Whoop, white precipitate, tertiary. Tertiary alcohol is present. 30 seconds later, I see a white precipitate, secondary. No white precipitate. Primary or not quite zeroary. For it to be zeroary, it can't be bonded to a carbon, right? How could I have an alcohol not bonded to a carbon in an organic compound? So no precipitate means primary or not an alcohol. There is no alcohol present. Right? So that's where this gets used as a classification test. Why would we not use it synthetically? Right? Let's assume that we have, I'm going to be annoying and use what the textbook uses, DCH3, DCH3. What would I expect for my product? Whoops. CH3. What have I just done to this question? I made a chiral center. Okay. Where is that chlorine going to be attached? Up here or down here? Option 2 or option 1? It is not the same position because spatially there are different orientations. That's left versus right hand because that's a chiral center. So you can't tell me 1 and 2 are the same.
Should be both positions.
It was a trick question. It's under SN1 reactions, which means we form a carbocation, which means the chloride can come and attack from top or the bottom equally. We get both products. Why would we not use this reagent synthetically? So I walk into the lab, I want to make product A. Why do I not use this reagent? I'm going to get A and A prime. I only want A, not A prime. So synthetically, they're pretty horrible reagents because we go through that unimolecular mechanism. Make sense? Okay. So go ahead. I'll give you 3 to 4 minutes. 4 questions, 4 minutes. So, in this chapter, one of our first things, because remember when we did the synthesis activity, right? We had to figure out which of the 5 reactions it did, which were acid base, substitution, elimination, addition, radical. Okay? Because we're in this chapter, okay, as long as we're focused on just this chapter, we can cheat on determining those 5 reactions. Because the chapter was called substitution and elimination. So we only have to focus on those 2. So we can use some kind of cues from our textbook and what we're talking about to eliminate some of our choices to make life a little bit easier. It doesn't always work, but it can work a little bit. Right? So all of these are looking at substitution or elimination, which again means we've got those 4 things that we have to be evaluating for substitution elimination, being leaving group. I can never make that mistake again. Nucleophile, substrate, and solvent. So we need to be thinking of those things when we approach this. Right? So we start the first one. We're doing a substitution, and it can help to go through and label your positions. So one of the first things that I went through and did, because the suggestion was made that carbon moved. Well, if you're concerned about the carbon, erase everything but carbon. Did carbons move? No. What did happen? We did a substitution, but we did the substitution kind of oddly. It looks like I really did a substitution of OH for hydrogen and bromine for hydrogen, all with just that reagent. That seems really weird. Okay. What type of mechanism did this fall under? SN1. And when we think SN1, we think carbocation. And when we think carbocation, you have to think about rearrangements. Rearrangements are not something you rely on for a synthesis. Okay? It is kind of an artifact. It gets in there and messes with things. So if you're running a synthesis, you say, oh, I can get this product because it rearranges to make this. You want to be very careful and typically avoid that. The only rearrangements that work for synthesis are ones that are tied to people's names because they worked that well. Okay? Rearrangements are really just like, oh crap, I'm not going to get a good yield now because it's doing weird stuff. Okay? This is doing weird stuff. We would protonate our good leaving group. The leaving group leaves, leaving behind a carbocation, which is secondary. I can then do the rearrangement, which I show with the curly Q, to get our tertiary carbocation. Now the bromide can come in. Make sense? The next one. How fast would I expect that reaction to occur? Maybe it's a substitution. Okay. Adding a strong acid. I'm making that a good leaving group by adding that piece, so that should be a good leaving group. Substrate is primary. Primary substrates favor SN2 mechanisms. What did we say the mechanism was for these? Our SN1 or our unimolecular. Okay? Which means the substrate doesn't favor the chemistry. If this one happens, it'll happen very slowly. The next one. I had concentrated sulfuric acid. Okay? So no nucleophile, so no substitution. That's reasonable. I predicted no substitution. Or I see no substitution. I see an elimination. So good. My reagent check says elimination. I get elimination. What's the issue with this elimination? What's that? Say that again? It looks like we had a rearrangement. Okay? We did the elimination to form an external double bond. Okay? More than likely what happened is we get this as our lost a carbon. Nope. No, we didn't. We would get that as a product. But that's not what we're getting. Why not? Well, what are we in the presence of? Concentrated sulfuric acid. We probably won't see the carbocation because the carbocation would have to form on a primary position. But in the presence of that concentrated acid, this reacts with acid to make a secondary carbocation. Now that I have the secondary carbocation, I can do a rearrangement. I probably don't form it outright. Okay? Last one. Sulfuric acid clearly was marked as dilute. Sorry, should have said dilute. Well, it says it now. Why did we get the result we've got? Why did we not get the elimination? The previous one had sulfuric acid, and I got an elimination.
Because we couldn't add in that hydrogen. It didn't have enough concentration to add in that.
Okay. If we're at a concentrated acid, we protonate all of them. What happens to our nucleophile? I've got none. If I'm at a dilute acid, I protonate some of them, which means I still have nucleophile. As long as there's nucleophile, I can do the substitution. Concentrated sulfuric acid gets rid of the nucleophile by sheer presence of the concentration. Okay? So a subtle change in the concentration can make a big change in the end result. Make sense? We're going to keep doing it. Ether synthesis. Okay? We just looked at that as an example. Okay? Within our ether synthesis, we need to make a good leaving group. Alcohols aren't good leaving groups. Okay? Or we could make a good nucleophile. Those are really the two options. Okay? So, first case, or for second one, I'll add a strong base. By adding a strong base to that system there, what am I doing? Making a good leaving group or making a good nucleophile? So here's my strong base. Name a strong base for me. Base. NaOH. So hydroxide. You give me the strong, just not the base. So our hydroxide, what is that negative charge going to do? React with a positive. Because I'm telling you it's acting as a base, we don't have to evaluate is it going to react with the carbon or the hydrogen. I told you it's a base, which means reacts with the hydrogen. Hydrogen then has too many electrons, so those electrons get shuttled to the oxygen. Did I make a good leaving group, or did I make a good nucleophile?
Nucleophile?
We draw out the result. We end up with a negative charge on that oxygen from step one. Is a negative charge a good leaving group? No, it's a horrible leaving group. I've made an awesome nucleophile. I can follow that reaction up with a step 2 of adding an alkyl halide. What chemistry is available to the alkyl halide? As a hint, there's only one of them, and it has something to do with that purple carbon, which I promise is purple. We can make it red. That red carbon acts only as an electrophile. What happens? Nucleophilic attack. We kick out our chloride. We now have carbons on both sides of the oxygen. We have an ether. This is known as the Williamson ether synthesis. Why did he get his name attached to such a simple reaction? I have no clue. Okay? Nothing about this looks tricky to me. So I have no idea why he gets tied to this. Okay? But he does. So you may hear people reference the Williamson ether. They're just talking about reacting an alcohol with a strong base. That turns it into a strong nucleophile only, and we can then add a good electrophile to it, okay, to swing it across. Okay. Where we will pick up on Wednesday is looking at a synthesis for those two reagents. We've got half the class, so left side of the class, so Shannon, Farzan, Elise, and Jenna. We'll take MTBE on the left-hand side of the screen. Everybody else, I'm tired of saying people's names, everybody else, we'll take anisole on the far right. Come up with a synthesis for those compounds. As a pseudo hint, there are two answers for both.